All right, today we're jumping into a huge idea, a concept that honestly lets us measure the real world in all its messy, changing, curving glory. We are talking about integral calculus.
So let's just get right to it. Look at this shape. See how the top edge is a curve? Your classic go-to formulas for squares or triangles, they just won't work here. So how in the world do you find its exact area? Believe it or not, this is the very question that had mathematicians scratching their heads for centuries.
And this really gets to the heart of the problem, right? A square? That's easy. We've all known how to find its area since we were kids. You just do length times width. Done. But that shape on the right with the curve, that curve means the value is constantly changing. And for that, well, we're going to need a much more powerful tool.
So how do we solve this puzzle? It all starts with a brilliantly simple idea. You could almost call it a mathematical superpower, the power of slicing things up. Instead of trying to measure this complex shape all at once, we're going to break it down into pieces we do understand.
Okay, so here's step one. We can't measure the curved thing, but you know what we can measure? Rectangles. So let's just try to fill up the area with a few of them. Now, it's not a perfect fit. You can see that. There are gaps, some bits are sticking out, but it's a start. It's a rough approximation.
Now check this out. What happens if we use more rectangles and we make each one a lot thinner? Whoa, look at that. The slices start to hug the curve way more closely. The gaps get smaller, the parts that stick out are tinier, and our estimate for the area is getting much, much better.
And here it is. This is the big conceptual leap. Just imagine, what if we could use not 10, not 1,000, but an infinite number of impossibly thin rectangles? I mean, so thin they're just lines. At that point, there are no more gaps. Our approximation becomes so perfect that it stops being an approximation. It becomes the exact area. How cool is that?
This whole idea, this powerful concept of summing up an infinite number of tiny things, it's so important it gets its own special name and its own symbol in math. This is where we finally meet the integral. Think of it as the magic formula that does all of that slicing and adding for us.
So, to put it simply, when you hear the word integral, all it really means is the mathematical process for doing what we just imagined. It's the tool we use for adding up all those infinitely small slices to find a total. And that total could be an area or a volume or, as we'll see, a whole lot of other things.
Now I know this notation can look a little intimidating at first, but let's break it down. It's actually pretty simple. That long, stretchy S symbol, that's the integral sign. It's basically a command that just means sum everything up. The f of x, that's just the specific recipe for our curve. And that tiny little dx at the end, that represents the incredibly tiny width of each and every one of our infinite rectangles. So you see, it's our entire slicing idea just written down in a super compact code.
Okay, enough with the theory. The best way to really get this is to see it in action. So let's take a pretty common curve, y equals x squared, and let's actually calculate the exact area underneath it.
The whole process is basically like a four-step recipe. It's super straightforward. First, we write the problem down using that integral notation we just learned. Second, we do the main calculus move, which is called finding the antiderivative. Third, we plug in our start and end points. For this problem, we're going from 0 to 2 on the x-axis. And finally, we just subtract to get our answer.
And when we run that function, y equals x squared, through that four-step process from x equals 0 to x equals 2, what do we get? Boom! 2.67. That's it. Not an approximation, no guesswork. A perfect, precise answer, and it's all thanks to the power of the integral.
So we can find the area under a curve. That's pretty neat. But why does this matter so much? I mean, why is this considered one of the absolute cornerstones of modern science and engineering? What is this all for, really?
Well, because finding the area under a curve is just a visual way of saying calculating the total accumulation of any changing quantity. And once you realize that, you start to see that integrals are, well, they're everywhere. Physicists use them to figure out how far a rocket has traveled. Engineers use them to design bridges and dams. They're used in finance to model how investments grow over time, even in computer graphics to render 3D shapes, and in medicine to measure blood flow. It's amazing.
You know, this quote from Galileo just captures it perfectly. The universe isn't built out of simple, static shapes. It's in constant motion. It's always curving and changing.
The integral gives us the language to actually describe that dynamic reality with absolute precision.
So, if there's one thing to take away, it's this. Integrals give us this incredible method to solve ridiculously complex problems just by breaking them down into an infinite number of simple little pieces. It really is a mathematical superpower. Which, of course, leads to a final question for you. Now that you know about this tool, what seemingly unsolvable problem would you want to tackle with it?